Please make sure you have your copy of the assignment, What Does Light Tell Us About Atomic Structure? In the first part of this activity, we looked at light emission and absorbance by materials as a way to introduce the idea of electron orbitals. The way that energy interacts with matter tells us a lot about how electrons are arranged into orbitals in atoms. What we're going to do next is look at some examples of how to write a configuration formula that describes the arrangement of electrons into these orbitals. So we'll look at these examples together. I'll be referring to the periodic table. There's one on the last page in your handout. You can go ahead and tear that out so that you have that handy to look at. And after we've done some examples, then you can work on the problems yourself. So when we're doing the examples, we're going to use this template which shows the arrangement of electron orbitals by increasing energy. Each of the circles here represents an electron orbital, a place where either one or two electrons might be found in the space outside of the nucleus. The numbers in front, the principal quantum number, describes the energy level of that electron orbital. The energy level can be thought of as describing something about the size of the electron orbital. The bigger the number, the bigger the relative size of that orbital compared to the other orbitals in the atom. The letters describe something about the shape of the electron orbital. S orbitals have a spherical shape. There's one type of S orbital because there's only one way you can point a sphere in 3 dimensions. P orbitals come in different shape. They look kind of like a dumbbell or an hourglass. They have 3 different directions that they can point in space. There are 3 different kinds of P orbitals at any energy level. D electron orbitals have a more complex 3-dimensional shape, and there are 5 different ways that D orbitals can arrange in 3-dimensional space. F orbitals, which aren't shown here on this diagram, there are 7 different ways that they can arrange. What we'll do is we'll start by looking at the periodic table, finding the element that we're working with, and identifying the number of protons and electrons it has by looking at the atomic number. With each element on the periodic table is listed its atomic mass, which we referred to when we were doing our stoichiometry unit. Now we'll look at the atomic number. That's the whole number. As you go across the periodic table, the whole number, the atomic number of the elements increases by 1 for each element. That counts the number of protons in the nucleus of the atom. Protons have a positive charge, and it's the number of positive charges which identifies which element you're working with. In the elements as they're listed on the periodic table, they have the same number of protons and electrons. So the atomic number also counts the number of electrons in the space outside the nucleus. That's what we're going to focus on now. Electrons are what give elements their particular chemical properties, and also many of the properties of compounds that are formed when atoms join together. So let's look at the examples. The first example is for the element fluorine. So I'll do fluorine first, and you can write down how I do this along with me. Fluorine. I'm going to find fluorine on the periodic table. Fluorine has an atomic number of 9. So that means it has 9 electrons. I'll use the letter E for electron and the negative sign for its charge. 9 electrons. Those electrons are arranged in orbitals by increasing energy. Each orbital can hold as many as 2 electrons. So I'll start with the first electron in a 1s energy level orbital. And then the second electron can go in that same orbital. Now that electron orbital and that energy level are filled with electrons. I'll write down 1s, and I put 2 electrons in it. 1s2. The second energy level electrons, 2s, there's room for 2 more electrons. 1, 2. So I'll write 2s2. I've still got how many more electrons? I've used 4. I need 9. I've got 5 more to go. I'm going to put the 5th, 6th, and 7th electrons in the 2p energy level. There are 3 different directions that those electrons can arrange. I put them into separate orbitals first because electrons have a negative charge, and like charges repel each other. These electrons want to be as far away from each other as they can in that energy level, so they spread out into different orbitals. Before we pair them up, we give them their own empty orbital. So that was 5, 6, 7. Here's number 8 and number 9. So I just put 5 electrons into the 2p orbitals. The numbers on top count the number of electrons. That should add up to 9. The numbers in front tell how big the energy level is, or what its relative energy level is, and the letters describe the shapes. Sphere-shaped s orbitals, dumbbell-shaped p orbitals. Fluorine. Now, when you learn how the periodic table works, you'll be able to understand what this formula really means. When I look at this formula, what I see is an element that reacts by gaining electrons. It will gain one electron to become stable, like a noble gas, and form a negatively charged ion. That's something that you can tell by looking at this electron formula. You can also tell where that element is on the periodic table and what other elements will have similar chemical properties just by looking at that formula. Let's do the next one. The next example is for the element silicon. If you find silicon on the periodic table, it has an atomic number of 14, so that means that it has 14 electrons. And I'll put those electrons into the electron orbitals by increasing energy. The first orbital, the 1s orbital, I have room for 2 electrons. So I'll put 2 electrons there, 1s2. The next orbital, 2s, there's room for 2 electrons. So I'll put those 2 electrons here, 2s2. The next orbital, the 2p orbitals, we have room for 1, 2, 3, 4, 5, 6 electrons. So 6, I've counted up 10 electrons so far. In the 3s energy level orbital, I'll put 2 more electrons. 1, 2. Now I'm up to 12 electrons. And here's 13 and 14. They go into empty orbitals before we pair them up. So 3p2. When I say empty, I don't mean that the orbitals are already there waiting to be filled. What I mean is that the orbitals describe the space outside the nucleus, and there's space for 6 electrons in 3 different orientations in the space outside the nucleus at the 3rd energy level. It's not like something that's waiting there to be filled up. It's a space that the electrons go into outside the nucleus. So if I count up these numbers here, they should add up to 14 electrons for silicon. All right, let's do another example. The next example is vanadium. Vanadium is number 23 on the periodic table, so it has 23 electrons. And so I'll put the first electrons into the lowest energy level. I can put 2 electrons here. And then the next energy level, there's room for 2 electrons in the orbitals that can be at that energy level. And then 2p electron orbitals, there's room for 6 electrons. So I'll fill that level up with 6 electrons. I've used 10 electrons so far. And then 3s, I can put 2 electrons there. 3p, I can put 6 more electrons here. 3p6. Okay, so how many have I used? I've used 18 electrons. Then I can go to 19 and 20. 4s2. And then I've got how many more? I've got 3 more to go. So I'll put 1, 2, 3 electrons at the orbitals of the 3d. 3. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. The electron configuration formula for vanadium. When you look at this, what it really describes is a picture of how the electrons are arranged in orbitals of increasing size or energy and different shape, and how many electrons are found in orbitals of that particular size and shape. Okay, let's do the next one. Zirconium. Zirconium is element number 40 on the periodic table. And so, I can tell just by looking up here where it's going to end. I could count by 2 for each of these orbitals to get a sense of where it's going to end. 2, 4, 10, 12, 18, 20. This makes 10 electrons. That would be 30, 36, 37, 38. And then the next 2 electrons would go into 4d orbitals like that. So I could put 2 electrons here, 2 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 34, 35, 36, 37, 38, 39. I lost count somewhere. Okay, let's do the last example, zirconium. Zirconium has 40 electrons. Now, you can use this diagram right here to quickly determine where the electron configuration is going to end by counting by twos. There could be 2 electrons here, 2 more here. Each of these orbitals can hold 2 electrons. This would be 10, nope, 2, 4, 6, yep, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I'm up to 20 here. There are 5 orbitals with room for 2 in each orbital. So I have 10 more electrons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm up to 30 electrons. 31, 32, 33, 34, 35, 36, 37, 38. Now I've got 2 more electrons to make 40. 39, 40. So I could quickly figure out what the electron configuration is going to be. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. Okay, so the electron configurations for the elements also show an underlying pattern on the periodic table, which we'll look at next. But first, you'll want to make sure to do the problems. There are 20 problems, and there's room for 20 problems on the front and on the back. When you do the problems, be very careful. The problem number is not the same as the atomic number for the element. Once you get past problem number 5, element number 1, hydrogen, is problem number 1. And this is element number 2, 3, 4, and 5. But once you get to problem 6, oxygen is not element number 6. Oxygen is element number 8. So look at the periodic table so that you know which atomic number to use. Argon here, problem number 12, that's not number 12 on the periodic table. It's number 18 on the periodic table. Likewise, zinc is element 30. It's not element number 16. Element 16 is sulfur. So don't get confused by the number of the problem. Use the numbers on the periodic table to tell you how many protons and electrons to use when doing the electron configurations. All right, we'll get back and look together at the periodic table and a pattern that obtains from the last electron orbital that you write for each configuration formula.